In science, we build models to understand the world, but as statistician Richard McElreath points out, these models are like golems, mythical clay robots built to follow orders. They are incredibly powerful, computing equations flawlessly, but they are completely mindless. A statistical model doesn't understand cohesion, physics, or biology. It only understands the mathematical instructions we program into it. And for nearly a century, the primary instruction we've been giving our golems is a framework called null hypothesis significance testing. But what if the very logic of this framework is creating an illusion of truth? In traditional frequentist statistics, we are taught to play a game of falsification. We start by creating a straw man, the null hypothesis, which usually assumes that nothing interesting is happening and our data is just random noise. We ask our golem, if the null hypothesis were true, how unlikely is this data? If the probability, the p-value, is small enough, we reject the null, we destroy the straw man, and human nature takes over. Because we killed the null, we confidently declare that our alternative hypothesis must be the absolute truth. But this is a logical trap. It assumes the world is a simple binary choice. It assumes that killing one idea proves another. Hypotheses are just vague ideas. To test them, we must translate them into process models, specific physical stories about how the data was actually generated. This is where the frequentist logic breaks down. The world is tangled. Multiple completely different process models can produce the exact same statistical data. Imagine you run an experiment, and your data perfectly matches statistical model 1. If you simply reject the null and celebrate, you are blind to a massive problem. The data is perfectly consistent with your alternative theory, but it is also perfectly consistent with a completely different version of the null. When multiple physical realities lead to the same mathematical outcome, falsification fails. You haven't proven your theory, you've just ignored the other possibilities. This is why we need Bayesian statistics. The Bayesian approach doesn't treat science like a courtroom where we try to execute a single null hypothesis. Instead, it treats science like a competition of stories. We put all our process models on the table simultaneously. We start with a distribution of belief. As new data arrives, we don't make binary choices to accept or reject. Instead, we simply reallocate our belief. The math automatically gives more probability to the stories that predict the data better. If the data is consistent with two completely different stories, the Bayesian golem doesn't force a fake conclusion. It splits the belief between them. The resulting probability distribution becomes wide and flat. Instead of ignorant certainty, the Bayesian framework returns high variance. It mathematically signals its own ignorance. It tells the scientist, multiple stories fit this data, I need more evidence. The need for Bayesian statistics isn't just about calculating different numbers. It is a fundamental shift in scientific philosophy. It is the realization that to find the truth, we must stop trying to destroy single ideas and start honestly measuring our uncertainty across all of them.